Welcome to this video about mesh generation for flox-GPU. I will show you how to use the program meshmaker to create a mesh for flox-GPU. We're going to look at the workflow really quickly. Flox-GPU works on grids. However, input data is often provided in vector form, such as points, lines, or polygons. In this video I'll show you how to convert this data to a mesh for flox-GPU. It's basically a two-step process. First we convert the vector data to a triangulated irregular network. In a second step we convert this tin to a grid. We're going to do this for a small area as our example. It contains fields, houses, streets, and a river. The first step is data preparation. You need to use some sort of GIS. We're going to be using ArcGIS, but any system that handles your shapefiles is fine. We start out with a boundary, which is a closed polygon in our case, and add the break lines we want to have in our final mesh, one after the other. You can see we already clipped these to be completely within our boundary. It's important to notice that all this data is true 3D data, meaning we have X, Y, and Z values on every vertex. We'll also be adding buildings in the form of polygons. We're going to be having a polygon at ground level and one at the roof level. The step of data preparation is all about making sure a simple and clean topology is reached, meaning you don't have overlapping segments, you don't have touching segments except on a vertex, which is an example here, and you don't have crossing segments. So our data is pretty much clean already, but the data preparation step is there to do this, because otherwise the triangulation is going to fail. You can also see we used a buffer when we clipped our input data, so it doesn't touch the boundary on a segment without a vertex. To recap, we need a boundary which should be 3D data. All data for the mesh needs to be within this boundary. We're working on Esri shapefiles, and all the data has to be 3D once again. Topology, no overlapping lines, no touching or almost touching break lines. All line intersections need to be at a vertex. After finishing the data preparation stage, we start meshmaker, set our project up, and we begin by loading our vector data into meshmaker. Once again we start out with the boundary. You can load shapefiles one by one, or you can do a bunch at the same time. We're also going to include the point cloud, which I forgot to show in the data preparation step. It is a filtered cloud of an airborne LiDAR survey. Note that point clouds, especially LiDAR point clouds, can be really big, and they often are too big for meshmaker to handle them. As a rule of thumb, 4 million points can still be done. If you have more than that, you'll have to try, and maybe it's advisable to filter out your data some more, or you need to find other ways to create your mesh. For example, divide it up in several smaller meshes and then stitch those together. One of the benefits of using meshmaker is that you can work it in parallel with your GIS. So if you alter break lines like I just did here, you can simply reload the table of contents of your project, and it will reload all the shapefiles again, and therefore whatever you altered is going to be altered in your project as well. If you're going to be using roughness values in your hydraulic simulation, you need to provide a grid that contains the value for every cell. And this grid has to be aligned with the mesh, the DTM mesh you're using. Therefore, we included a step to create this roughness grid in the process of creating your DTM mesh. So what we're doing is we have a coverage, a ground coverage with different roughness values. They are called Strickler values. And we have a shapefile covering all the areas. You see this shapefile is not aligned with the DTM boundary. It doesn't have to be, because meshmaker will cut it to the right size. Now we select this prepared polygon that contains these values, and we select the field that has the values. In this case it's called KST, the field. Then we simply select an output path where it's going to put both your calculation grid, or just your mesh, and your roughness value mesh. We need to select a grid resolution or cell size, which is the crucial step. You can measure distance by holding control in meshmaker and dragging your mouse. And we see at this particular spot it's about a meter wide, so we're going to be choosing a grid resolution of 0.3 meters. We choose brake line enforcement as highest brake line, and we hit the make button, because this is all we have to do for now. And in the background it composes our mesh. Depending on the data, this can take a while, but for us we don't have a lot of data in this example, so it's done relatively fast. There is no message in meshmaker about the completion, but you will find your mesh, if everything worked out, in the output path selected. Here's a short recap of this step. You load the vector data. If applicable, you select a file for Strickler roughness. You specify output path and cell size, and you hit. If successful, meshmaker generates 3 main files: the DTM grid, or mesh as we call it, in a TIF format, a hillshade of this mesh, and if you selected one, a roughness grid with the Strickler values. Here's a look at the output of our example. This is the 3D vector data we loaded, and we're going to load the grids. You will notice that the crucial step, apart from data preparation and reaching a clean topology, is the selection of the cell size, because you want to have your cell size as big as possible to have fast running simulations on flox-GPU, but you need it to be as small as necessary to reflect the DTM data that you include in your project. So if you have very small structures, you usually will need a smaller cell size. Upon loading our resulting grids in ArcGIS, we notice that there is an issue with the minimum maximum values. We believe this to be an issue of ArcGIS. You can fix it by calculating statistics, and then you'll see that the DTM grid or mesh displays the elevation data nicely. Our roughness grid simply displays the values given by the polygon coverage we use to create it. You can check this if you superimpose both vector data and the grid. Let's take a look at the steps so far using a 3D visualization program. This is the vector step, basically our input data. You can see the roofs ground level and roof level polygons of our buildings. This is our creek, the street, 3D vector data basically. And in the first step, we create the TIN, the triangulated irregular network, and this is what this step looks like. And in the second step, this TIN is mapped onto a grid, which is what you see here. Now I'm going to show you a small feature that I included for demonstration purposes. I digitized a small wall into our vector data, and because we selected highest break line in the break line enforcement dialog of meshmaker, this feature is preserved through all the steps, even though the extent of this wall in X and Y direction is actually smaller than the cell size. So breakline enforcement in this case allows you to have the cells that are crossed by this high line to be at the height of this line, while otherwise they would simply be mapped exactly on the surface. So this is a way to preserve very small elements, even though your cell size is not sufficient for those elements. So this is the final mesh on which we are going to run our simulation. Thank you for watching.